Hello everyone, I am Dr. Anita Thomas. Today's lecture is on section 1.8 first order differential equations for the 5th semester B.Sc mathematics students. We are following the text Differential Equations Theory, Technique and Practice by G.F. Simmons and Stephen Kranz. So we shall move on to section 1.8. I am going to discuss about some differential equations of the form m of x comma y dx plus n of x comma y dy equal to 0, which are plainly not exact. But we can find out some suitable functions known as integrating factors. By multiplying the given equation m dx plus n dy equal to 0 by these integrating factors, we can make it exact. For more details about exact equations, do watch my previous videos. So I have given a short definition of exact equation. The structure of exact equation is like this: m of x comma y dx plus n of x comma y dy equal to 0, and is exact if it can be written as the partial derivative of a function f of x comma y with respect to x into dx plus that of with respect to y into dy equal to 0, or that equation can be represented as a total differential of a function f of x comma y and its solution is f of x comma y equal to c if it exists. Now integrating factors. Some equations are not exact, may be multiplied by some factor, a function say u x of x comma y, to make them exact. This function u of x comma y exists. It is known as an integrating factor. It will make valid the expression dou partial u into n of x comma y by dou x equal to dou u into m of x comma y by dy. That is, the condition for exactness will satisfy on multiplying m and n with respect to with the u. There are three types of such integrating factors mainly. First one, u of x comma y equal to x raised to m into y raised to n. The second type is u of x comma y equal to u of x. That is, u of x comma y is a function of x alone. Suppose if you are getting a constant, say 2 here, then 2 can be written as 2 into x raised to 0, which is a function of x. So if u of x is a constant, it may be considered as a function of x alone, or in the second case it may be considered as y alone. So these are the three types of integrating factors. I shall explain the three cases using examples. So first case, integrating factors using u of x comma y equal to x raised to m, y raised to n. So in this first problem, the integrating factor will be of the form x raised to m, y raised to n. So example 1, y square plus 3xy cube into dx plus 1 minus xy dy equal to 0. But m is this term and n is this second one, 1 minus xy. Now dou m by dou y is 2y plus 9xy square, and dou n by dou x is minus y. See, they are not equal. Therefore, the given thing is not exact. Now, we will try to make it exact by multiplying the equation with the x raised to m, y raised to n. So on multiplication, the given equation becomes x raised to m, y raised to n plus 2 plus 3 into x raised to m plus 1, y raised to m plus n plus 3 into dx plus the second term becomes, here it was 1, it becomes x raised to m, y raised to n minus x raised to m plus 1, y raised to n plus 1 into dy equal to 0. See, this is m and n is this quantity. So what is dou m by dou y? It is n plus 2 into x raised to m, y raised to n plus 1 plus n plus 3. See, here is a 3. This is y raised to n plus 3. So y raised to plus 3 into n plus 3 x raised to m plus 1 y raised to n plus 2. Now n equal to, now dou n by dou x is equal to, n is this one, dou n by dou x is equal to m into x raised to m minus 1 y raised to n minus m plus 1 x raised to m into y raised to n plus 1. Now, we want to make this equation exact by assuming that dou m by dou y equal to dou n by dou x. So, we assume this condition and we write these two equations as n plus 2 into x raised to m y raised to n plus 1 plus 3 into n plus 3 x raised to m plus 1 y raised to n plus 1, that is dou m by dou y equal to dou n by dou x, and we rearrange the terms and summing up the like terms we get such an equation. Now this is equal to 0, that means the coefficient of each expression in x and y, that is in the first one it is x raised to m, y raised to n plus 1 should be equal to 0. Then the second term it is x raised to m plus 1, y raised to n plus 2. Its coefficient is 3 into n plus 3 equal to 0, and last m is equal to 0. Thus we get such a situation which implies that m equal to 0, and substituting the value of m here we get n as minus 3. So what is the value of the power of x, which is 0, and the power of y is minus 3. Thus we obtain the integrating factor as y raised to minus 3. Now multiply our original differential equation by y raised to minus 3, getting this expression, which implies y raised to minus 1 plus 3x into dx plus y raised to minus 3 minus x y raised to minus 2 into dy equal to 0. And now we have to check for exactness again. So m is equal to this one and n is this term, implies dou m by dou y equal to this one minus y raised to minus 2, and dou n by dou x equal to again minus y raised to minus 2. See, now the equation, the given this equation becomes exact. So by multiplying by this integrating factor, we can make the given differential equation, which was at the first stage not exact, is now made exact. Now the procedure to find out solution. So solution is f of x comma y equal to c. So from but f comma x f of x comma y is equal to integral of dou f by dou y into dy. So what is dou f by dou y? It is n of x comma y into dy, because this equation is exact, means it has a total differential form. So from that concept we write this, and which is equal to n. And on integration we get f of x comma y as minus y raised to minus 2 by 2 plus x y raised to minus 1 into, this is our arbitrary constants. As we integrate with respect to y, x may occur here as a function of x may occur here as a constant, or it may be some constant itself. So write it here. Then we have dou f by dou x. So we differentiate this one with respect to, partially with respect to x, giving from this one it is y raised to minus 1 plus derivative of gx with respect to x, g dash x. But we have dou f by dou x is m. So y raised to minus 1 plus 3x m equal to this one. From this expression we shall get g dash x as 3x. Now what is gx? Integrate this one with respect to x, giving 3 by 2x square plus c. Now f of xy is obtained as, f of xy is here, obtained as, using this we get minus half into y raised to minus 2 plus xy raised to minus 1 plus 3 by 2 x square plus c from here. And in our text we write the solution as f of x comma y equal to a constant. So we write the solution in this way. Now the second case, integrating factor using u of x comma y equal to u of x, a function of x alone. Again I am saying that u of x may be a constant. If u of x is a constant, then also we can consider it as a function of x. So remember this idea. So the expression in this case, the expression 1 by capital N into m dou m by dou y minus dou n by dou x is a function of x alone. Say it is z of x. Then the integrating factor u of x is obtained by e raised to integral z of x dx. Now go to the problem. This is the problem, 3xy minus y square dx plus x into x minus y into dy equal to 0. What is m? This one. N? This one. Implies dou m by dou y equal to 3x minus 2y and dou n by dou x is equal to 2x minus y. See, they are not equal. So as such, this expression is not exact. Now we shall try this case. And now 1 by n into dou m by dou y minus dou n by dou x equal to, from here you subtract these two, getting x minus y divided by n is x into x minus y, getting the answer as 1 by x. See, this is a function of x alone. So z of x is 1 by x and if is u of x equal to e raised to integral z of x, that is u of x is e raised to integral z of x is 1 by x, getting answer x. Now our next procedure is multiply the given equation by the if, namely x. So on multiplication we get the given equation as 3x square y minus xy square d into dx plus x cube minus x square y into dy equal to 0. Now our duty is to check for exactness. See, by checking for exactness, we got it as dou m by dou y equal to 3x square minus 2xy, and dou n by dou x is equal to 3x square minus 2xy. M is this one and n is this one. Now they are same, so the new equation is exact. Now our aim is to find out the solution. So f of x comma y is integral dou f by dou x dx. It may be dou f by dou y dy also. So here I took it as dou f by dou x into dx. That means integrating with respect to x. So yeah, what is dou f by dou x? It is m of x comma y. Now m is 3x square y minus xy square dx. On integration we get x cube y minus 1 by 2 into x square y square plus h of y. Here h of y comes because we are integrating with respect to x. Y, a function of y, may occur as a constant here. Now differentiating this f with respect to y partially, we get x cube minus 3 x square y plus h dash y. Now what is dou f by dou y? It is n. So we can equate this 1 to n. So x cube minus x square y plus h dash y equal to n, namely x cube minus x square y. So we can cancel these two terms, giving h dash y equal to 0 implies h of y equal to c, a constant. Now f of x y can be written as from this expression and this one. It is x cube y minus half x square y square plus c, and solution is x cube y minus half x square y square equal to c. So the next problem, next type is integrating factors using u of x comma y equal to u of y. In this case, the expression 1 by m into partial n by partial x minus partial m by partial y is a function of y alone, say z of y. This may be a constant value also. Integrating factor is u of y equal to e raised to z of y dy. Now example 3, y dx plus 2x minus y e raised to y dy equal to 0. What is m? Y. And dou m by dou y is 1 and n is this one, and dou n by dou x is 2. See, these two are not equal, therefore as such this is not exact. So we shall try to make it exact. So 1 by m into dou n by dou x minus dou m by dou y equal to 1 by y into 2 minus 1, that is 1 by y. So it is a function of y alone. So we took it as z of y, and u of y is e raised to integral z of y dy equal to e raised to ln of y, which is y. Now multiply the given equation by y, getting y square dx plus 2xy minus xy square e raised to y into dy equal to 0. Now check for exactness. M is this one, dou m by dou y is 2y, and n is this one, dou n by dou y dou x is, from here it is 2y. So these two are equal. So by on multiplication with the integrating factor, this equation becomes an exact equation. So we can solve it. F of x y x comma y equal to integral of dou f by dou x dx. Dou f by dou x is m of x comma y. From the equation, write m here. It is integral y square dx plus h of y equal to xy square plus h of y. Now, differentiating partially with respect to y, this expression we get dou f by dou y is 2xy plus h dash y. This one, 2xy plus h dash y. But dou f by dou y is our n. So, 2xy, these two, we can equate these this one and n. So 2xy plus h dash y equal to, what's n? N is here, n. So cancelling like terms, we get h dash y equal to minus y square e raised to y, which implies h of y equal to minus of y square into first function into integral of the second minus integral of derivative of the first 2y into integral of the second e raised to y dy plus c, that is minus of y square e raised to y minus, again we have to apply integration by parts here, getting 2y e raised to y minus 2 into e raised to y plus c. So f of xy is x square. You substitute these quantities in here, we will get f of xy, and it is obtained as xy square minus y square minus 2y plus 2 into e raised to y plus c, and it leads to the solution xy square minus of y square minus 2y plus 2 into e raised to y equal to c. So do these assignments. Thank you.